Go to week 1, or it says week 2 seminar notes, but I just need to change this to a 1. Because it's week 1 seminar notes now. Okay, so I'm going to be today sort of like walking through some notes that I wrote up about over some of the reading, and I interpolate some of my own stuff and whatever. So I'm going to walk through that because you guys didn't have the advantage of having read the first few chapters of this book before today, and I didn't want to lose, because we have this weird once a week class, I didn't want to lose a whole week. So I want to just go ahead and kind of like introduce it as we go, and we'll discuss, and then in the future seminars there will be less material that I will be presenting. I will mostly be presenting, here were a couple cool things that kind of complement the reading a little bit, and maybe here's a video, here's a this or that, and then we'll just be doing discussion questions. Okay. So we are going to start doing discussion questions though, so I'm going to go through it and then we'll start discussing, because since I'll have presented some material, we'll have something to talk about. So, defining robotics seems like probably going to be a pretty important start to our robotics and automation course. So the meaning of the word robot has evolved since its popular introduction in a Czech play in 1921. It's weird how words get made. Even preceding the coinage, people had long built machines that worked for humans. However, these were not robots in the modern sense. Here is a definition of robotics. So I have a qualification on this that I say, but it's not bad. A robot is an autonomous system which exists in the physical world, can sense its environment, and can act on it to achieve some goals. It's not a bad definition. However, it's a little unclear if that definition would include animals or humans as well. So I like to interpolate the word synthetic autonomous system, because an animal or a person can have autonomy as well. So I think synthetic is important. It's kind of pedantic, but I think it's important to make sure we use good terminology. A robot is autonomous in that, given sensory inputs, it chooses without any explicit user input how to act. Okay, so that's what it means to be autonomous. This eliminates many machines from the definition. However, the line is somewhat blurry, and there seems to be more of a spectrum of autonomy. Consider the scissors. Okay, a simple mechanism to be sure, but what separates it from a simple control system like a thermostat? Or, even simpler, a toilet, which has a float valve on it. So that's a simple control system. Could you say that there's a big difference between scissors and a toilet, for instance? So we'll talk about the thermostat though as a specific example. So the thermostat has sensor inputs, and it can turn on and off, or it can turn on and off a furnace, I should say. So you have that. It's a little bit autonomous. Like when it gets to a certain temperature, the person doesn't have to be standing there saying, okay, now turn on. It can turn on by itself. So that's cool. That's a step. The scissors couldn't do that, right? Scissors, if you left them with the piece of paper, they never would have cut that piece of paper, right? That's not something that's going to happen. But a human had to set the thermostat, and the basic if-then logic of the thermostat is hardly free thinking. I mean, it's really basic. So surely the human input is farther removed from the fully manual scissors, but there is, you can sort of see that there's this ambiguity there of what is autonomous and what is not. A system that a human had to program and set up in a certain way and set the temperature on and then can do something automatically afterwards, that is slightly autonomous.
Isn't that basically, though, how all of this is going to be done in the long run? You're going to give us a list of criteria, and then we're going to have set it up and programmed it ahead of time, and then it's going to have done it. So isn't it virtually going to have done the same idea? It would have had it programmed.
Yeah, for sure.
Then it can run on its own.
Right.
So it becomes autonomous to its extent that it's running on its own. But you still, even if it's more complex, you still have to set it all up programmed to tell it what to do.
Right. So, I mean, we're kind of flirting with a concepts of artificial intelligence as well. But what does it mean for something to be autonomous? Or how little control can we have on something before it becomes autonomous? And so I'll kind of try to distinguish a couple of things here. So something that is autonomous for a specific task can do a great job with that task, but it's generally not considered to be an intelligent agent because when we think of intelligence, we think of a sort of general purpose, ability to adapt to something that's new. So the thermostat, it could turn on and off for a long time depending on temperature. But if you immersed it in a bucket of water, it's not gonna function properly anymore. I mean, depending on how it's built, but it's probably not gonna function properly anymore. It won't know how to adapt to a new situation. Yeah.
What if your thermostat was just slightly more complex control, like proportional control instead of just like an on-off switch, right?
Right.
Now you're starting to get a little more adaptive.
It's a little bit more adaptive, right? It's able to do more things. It has more control over its environment. So it's getting a little bit more intelligent the more sophistication you introduce into it. But there is sort of this tension between autonomy versus intelligence. And I think that autonomy means like very little human intervention in this thing while it's running to do what it's intended to do. And then intelligence has this idea of adaptability and learning that most of the basic control systems that we make don't have. They don't have that ability to adapt to this new situation. However, some robots do, and we'll talk about that. We'll talk about how some robots can learn to adapt and can exhibit something that looks a little bit more like generalized intelligence. Whereas a lot of the things that we'll create in the more traditional engineering automation situations, they won't have that capacity. And it's fine, they don't need it. But when we start making robots, we start to think about how could they be more autonomous. I mean, you think about the robot that's wheeled robot. It's like it does great until it runs into an obstacle that it can't get over with wheels, right? Like
so
a bump.
Autonomous getting to the point to like where the Atlas is for that, the robotic systems for that.
Yeah, so it's getting very autonomous, meaning that there's nobody's flying it; it's flying
the
itself.
Atlas is it gets up and walks by itself, and then it traverses its own terrain and figures out how to cross different things.
Oh, what Atlas are you talking about?
It's a video I watched the other day. It was about it's a robotics company that's building it. Originally was just for the robot that they had that was actually able to stand up and walk upstairs by itself and come down and continue to work on it. Now it's traversing uneven terrain and doing other stuff and mapping it out by itself and getting to the point where it's actually going around and doing things by itself.
Yeah. So as it gets those capacities, it's able to be more and more autonomous. it's also increasing in intelligence. So they're very coupled, right? It's hard because if you have an agent that's sort of like set loose in an environment that's changing, it has to be both autonomous and intelligent to adapt. Whereas something in a very controlled environment might be fine just being autonomous. It might not need to be able to adapt. It might be able to go along just fine and do its little thing. Like a Roomba, generally speaking, it's not going to encounter too many, sinkholes or uneven concrete or things like that. It's mostly going to hit either a wall or it's going to hit a lamp. Pretty predictable things, and it's mostly going to be going over carpet or, whatnot. So there's different environments, different sorts of
might be way down with the payload
levels of autonomy. Yeah. I've seen those videos. The cat with the fin on it, riding the Roomba around. All right. So autonomy is that. Although we do not wish to introduce a physical other world dichotomy, we would like to require that a robot must exist in the physical world. Okay, so once you say that, it brings up all kinds of questions. Like, what do you mean exactly by physical? So I'll kind of get into that. So this requirement is there primarily to eliminate from consideration simulations of robots. So we kind of want to say a robot is not a simulation of a robot, or I should say a simulation of a robot is not a robot. Okay? And why might we care about that? I guess hold your thoughts, because we're going to come back to that at the end of the section. I'm going to ask that question. Of course, the pedantic at this point have a valid point. So does not simulation exist in the physical world? I mean, a simulation, everyone that I know of, runs on some sort of processor. It has a hard drive that could store the results of the simulation. Something that describes the robot, its trajectory, how it moves around. How is that different than a robot that's in the real world? It's kind of a good point. You could say that they're both in the physical world. However, what we really mean is something more like a robot can act on substances outside of itself. Okay, whereas a simulation is only going to happen inside of that computing system. It can't affect the world outside of it. A robot, when it's working, it can actually move a chair or knock over a lamp or probably just fall over. It can do all those things. In the world that we in general inhabit. So, we must take care not to limit robotics in our definition, but we also want to strive for clarity about what it means to be a robot. And in the end, what you find is that there's this sort of this spectrum of things. So in automation, control systems that a lot of manufacturers care about, for instance, there are lots of things, and including this platform that we're going to be designing in this semester. Like, is that a robot? Is a question that we might be able to answer. I mean, it's kind of hard sometimes to say what is and what isn't a robot, but I think that as we'll find, I think that the definition that we have is broad enough to include things like this robot or the platform that we're going to create. And not include other types of simpler mechanisms.
Memory foam?
Memory foam is probably not going to be considered. Although there are things that just by geometry alone are able to mostly I don't know if I can think of anything completely passive that can do it, but I'm gonna show you guys something in just a minute. That's gonna be kind of cool.
A windmill or something.
Yeah. So, okay. So here's another requirement. A robot can sense its environment, okay? So these are all coming from our definition. So, exists in the physical world, it's autonomous, can sense its environment. So, we typically separate user inputs from environmental sensations. So, if a user has like a button they can press, that's not considered to be a sensor input. That's considered to be a different type, a user input.
Would you consider a windmill sensing the wind blowing in the right direction?
I would say it's definitely affected by it, but and it could potentially be used as a sensor.
It starts turning when the wind blows on it, so it's
Right.
kind of a sensor, but it's.
I mean, it could be used as a sensor. I guess that's the thing, is if it's being used as a sensor, if there's something that's happening. So one thing that is required is it's going to sense it, but it's also going to have to act on its environment, which I think that the windmill doesn't really use that sensor information to act on its environment. Or maybe it does. So there are windmills that rotate into the direction of the wind. So maybe it is using that as a sensor, and it is actually adjusting its angle into the wind, which would be actually pretty close to our definition of a robot. It doesn't do a lot to its environment, though, so that might not quite make the definition. It's like right below the cut. It doesn't really do much to the environment. It kind of passively does. The wind blows through
What
it.
if it's like pumping water or something?
If it's pumping water, it's definitely, yeah. Then it definitely could be considered a robotic system by our definition, very broadly, because it's got to be autonomous, so it's autonomous. It's in the physical world, can sense its environment, loosely speaking. But I mean, if it's using that information to do something, then that's valid. And
What if it's just entirely a mechanical response? There's no electrical.
you can have entirely mechanical response as long as. So, for instance, I would say that the toilet float is doing something with that sensor information, right? It's not passively experiencing this flotation. It's using that flotation to affect something. And if the windmill is being blown, but it's using that blowing to turn into it and pump water, then it would be roughly robotic. I mean, it's pretty loose to call it a robot, but it is kind of a robot, yeah. But I wouldn't say your average Don Quixote windmill. It's not a robot. However, I could be wrong. I don't think that any of those old ones would turn into the wind or anything. But maybe they could.
Some of the old ones could.
Really?
I know for a fact, but I can't remember
Huh.
which one they were.
Maybe that's so possibly even the old windmills. Okay, and the other thing is it has to act on its environment to achieve some goals, right? So it's going to require some sort of actuator to do something. Now, if our robot just acted on its environment at random, it would totally suck, and we'd probably tell it it's no real robot at all. Therefore, we say that a robot must act on its environment in order to achieve some goals. So it must act on its environment, not just randomly, but it's got to do something that we want it to do. All right. This is why artificial intelligence is such a big deal. It allows the robot to be increasingly autonomous and yet exhibit some sort of rational behavior, even though you don't need to go very far to exhibit some sort of rational behavior, as we'll discuss later. So here are some questions that we can discuss. So why might we want to differentiate between simulated and real robots so sharply? We sort of hammered on that. Why do you guys think we care? Yeah.
Physical world is much more complex. You can have irregularities in your environment, gravity, friction, that kind of stuff. Things that you
Yeah.
can't build into simulation.
Yeah, so if you simulate it, I mean, you could try to simulate all the effects that are there, but it's hard to get them all, right? And almost always we forget about something that should be in it.
Really just your theoretical model versus your actual observations.
Mhm.
Because all of the simulations that we do are just theoretical models. They have to do just the formulas that we have, and none of those expressions which can complicate ever are exactly the same.
Yeah. Yeah, I mean, even I think that making sure that we have that, like that real, that the noisy buzzing world that exists out there. It's so easy to gloss over it. I mean, we do this constantly. We like simplify things, right? So when we think, okay, what kind of environments might this robot be in, and we try to build it into a simulation, even if we have really advanced physics simulators and all that, which there are, I flirted with. There's this one that is totally open source and is really cool, and I have a student doing it, a grad student working on it for me. But I can't. It doesn't install on Windows. It requires a Unix system, a Unix-based system. So it works on Macs. It doesn't work on PCs. So I didn't have any other Macs to put here, but if we had an extra one. Anyways, it's called Morse, like Morse code. It's pretty cool. Yeah, I like it. Uses that Blender 3D graphics engine, and so it's like all open source, but and free, like a puppy, as they say, is free. Not my puppy, but other puppies can be free, and free like a puppy means it's a lot of work, even though it's free. Okay, so what is intelligence? So let's just like figure that out, just now in discussion. You don't have to raise your hands. We can just talk.
Being able to make a decision, that's intelligence.
The ability to make a decision based on input
Mm-hmm.
to achieve a goal.
Like a rational response.
Yeah. So I like these ideas. What expand on rational though?
Like, not random.
Mm-hmm.
So there's some sort of reason, and it's maybe organized,
Mhm.
where you get consistent responses for
Code
consistent inputs.
Mm-hmm.
I feel like intelligence would be making a decision for its own benefit. Because if it makes a decision just to fall off a cliff, that wasn't very intelligent, right? But if it saw the
Didn't
cliff
say
and
it
went,
had
oh,
a
I
lot
don't
of
want to do that,
intelligence.
that's pretty intelligent.
So some sort of self-preservation, is that kind of what?
It acts, I'm trying to say that. I guess it acts for its own benefit,
Mhm.
regardless of, like, with some autonomy, right?
Wouldn't that be the development of your AI system? So like originally your AI systems are going to just be, you're going to have basic logic code that they follow, and they're going to have some value of intelligence that they can do, make decisions based on their environment and make qualitative, like, all right, this is the better of two different things that I've got. Neither of them are perfect, but this is the best that I've got. And then as you're developing, then you get more to like your self-preservation. That's a huge leap from just being able to say that you could just differentiate between two things and decide about it. To then also make it self-preservation and or beneficial to itself. How does it know what itself is and what's beneficial for itself, so it can make those decisions?
Yeah, I guess I don't want to confuse, like, I don't think self-preservation is where I was going with it, but it's really, let's say yours is a goal. The robot has to go to this position. Now its benefit would be to achieve that goal somehow. So the intelligence would be a better decision towards that goal instead of a pre-programmed if or that both choices don't meet that goal, right?
That sounds like learning.
Self-writing.
Yeah.
Ability to learn.
Yeah.
which would require like memory
Retain knowledge.
to be able to remember what previous decisions were good or bad.
Yeah, I mean, certainly if we see something, I would like to think of examples of like, what have I seen that I'm like, that wasn't very intelligent? And what have I seen that was like, oh, that was really intelligent? And I think, especially when you look at animals, and you can kind of like see like the wheels turning, and you can kind of see them figure something out. That seems to me to be a really good way to get a grasp on what we find to be intelligent or not. There are really low animals, they're like the insects, that will see something happen that will definitely kill it. And it will not change course. Like, I mean, you can like sit there and go bam, like this, and the thing will go walk right into it. Like if it was very intelligent, it wouldn't do that, right?
I recently saw a bird get hit by a truck. It was the bird was just standing in the road, and the truck just ran over it.
Yeah.
A lot of feathers.
Yeah. Fortunately, most birds are a little more advanced than that. And they've learned. I mean, so go ahead. Yeah.
Well, what about like bees, which are more intelligent than most insects, but they don't understand glass. So most of them will just simply continue to ram a window, whereas the wasp, really stupid, or a fly will just hit. What was that, a gap? And it will eventually go through.
Huh.
So
Interesting. Yeah. So the different sorts of intelligence that.
I've seen people do the same thing where there's an easy solution and they just keep hitting the glass window.
Yeah. Yeah. We're prone to this too, and
There's
it's.
a falcon near
It
my house
depends.
that keeps flying into the window because they're after my cockatiels.
Well, that just looks like bait to them. One of these days, that's going to be an open window.
Except that window doesn't open.
Maybe if they keep hitting it, it'll break.
It's double pain. Good luck.
Yeah. I think a lot of those things, and memory too. So memory is something that we notice in an animal when it's like, okay, I've seen this before, and this is the decision that's better. Like, I tried 15 different things, and this was the one that was best. And you'll see animals do that. And there's even a theory that I was reading about how ants find their way home. Do you guys know how they do that?
Most of them use trails.
So they do leave pheromone trails wherever they go, and there's an interesting thing about emergence that we can talk about. Ants are really cool, but they actually one of the problems is with ants is that they're everywhere, right? So I don't know that they can necessarily pick up their own scent trail back, and they'll go long distances, and it's very unclear sometimes. For a long time, it was unclear how they found their way back. And you can like take one a ways away, and it'll find its way back. How does it find its way back? And the theory is, and they've done a lot of tests, and I think it's correct. The ants can understand direction based on polarized light, so it can like roughly navigate using polarized light, so it can go long distances towards where its nest is using that method. But then when it gets close, that method's not precise enough, and they can't find exactly where it is. And they have this. I mean, who knows what it's like from the ant's perspective, but they made robots that could find like the home base based on these two methods, and they think that they look like ants when they do it. So they think maybe it's like this. So it's called the picture theory, I think. When the ant leaves the nest, it like remembers what it looks like from the exit of the nest. Like there's like an internal image that it creates. Like it looks like this. Okay, and then they go out, they do their thing, and then they rough navigate back, and then they start to try to navigate to where it looks like their internal image looks like the environment they're now experiencing. They try to match them, and that gets them the rest of the way there. And they try to make the two pictures look, because it should look similar by the time they get close, and then they try to match them. And that's the theory on how ants get home. They do leave pheromone trails, but that's not the leading theory, at least, on how they get home. At least as of, I think 10 years ago is how old this book is that I'm reading, so, yeah. Yeah?
I don't think intelligence necessarily needs to be like self-preservation or anything like that. So I have my vacuum cleaner at home is called a Nito. It's Nito Robotics. It's a robotic controlled vacuum cleaner, so but like a Roomba. So a Roomba hits a wall and then bounces, hits another wall and bounces, and it's got a couple of sensors in it, but for the most part, that's how it operates. My robot comes out of its bay, scans its area around it, and then says, okay, I'm going to go around the perimeter first, and then I'm going to go back and forth and do the inside in a orderly manner. I would argue my robot is more intelligent than the other robot. So is it really the robot that's intelligent, or is it the person that's programming the robot that is now intelligent? But so like with our project,
That's a good question.
if we are recording or doing a dynamic response to the object falling versus one that doesn't do a dynamic response, I would say the dynamic response is more intelligent than the non-dynamic response. So intelligence within bounds, I guess.
Yeah.
It's all relevant.
Right. I mean, I think that we tend to place a lot of value on the higher level intelligence that humans have, but it's funny because one of the problems that AI people have had is that they can make AI things do stuff that we find really hard to do really easily. I mean, you think about it, a calculator is kind of like this amazing AI machine, right? It's like you tell it to do this thing and it's like this math genius that just always gets the right answer. It's kind of amazing. But I don't think anybody's ever been like in awe of the intelligence of their calculator. And I think that one of the things that I've been reading about recently and is really, I think, resonates with me is that it's the sort of generalized aspect of the intelligence. It's like sure, it can compute the numbers, but like it can't do anything else. And I think we can find a very my puppy Niles last night so there's this whole thing now, like you got to figure out how to like train your puppy. I didn't even know there was a whole thing. There's like this whole literature on it, and there's like the old school like beat 'em and shit, and then there's like the new school that's like never ever say anything mean to them. So I don't know, but one thing I noticed was the puppy kind of likes to chew things. And walked up to the quilt on our bed last night while I was like laying on the floor prepping for class, and he just walked up to the bed and just grabbed the comforter with his teeth and started to pull. And I was like, no. And I was like, no. Here, I grabbed his chew toy and I gave him his chew toy, and he chewed his chew toy and he walked over and he plopped down and chewed his chew toy like on the spot over there. And then about 5 minutes later, the puppy is a little rambunctious, kind of like running around, and I see him sort of take the same angle at the bed. Like he's just, I could see him thinking, "Ooh, that looks like fun to bite again." And I don't say anything. He just kind of like opens his mouth, so like puts it on there, and then doesn't really bite down though, and walks over to the chew toy, grabs it, and plops down in the same spot. And I was like, smart dog. Like I was like, oh my god, intelligence. And that like really like low level of ability to adapt to something And now that puppy could never multiply 2 and 2 together, okay? So the calculator in some ways is way beyond the puppy, but the puppy could kind of adapt to that. And so one of the things that's been happening in the AI community is it's been starting to turn more towards basic intelligence, how to navigate the world, how to operate in the world, with just really basic mechanisms and basic ideas. And it's interesting how things that look intelligent emerge much quicker. So, all right. So I think we talked about how an animal might display intelligence now. And I think we probably covered how a robot might display intelligence. So let's get into the history of robotics. The practical possibility of robotics is based on developments in 3 fields: controls, so control theory, cybernetics, and AI, artificial intelligence, okay? So control theory, the standard definition of it, which comes from your Nice book, I think, is a control system consists of subsystems and processes or plants assembled for the purpose of obtaining a desired output with desired performance given a specific input or specified input. So that's a pretty standard definition. So the following block diagram is helpful when considering this definition. So you put in an input stimulus, you tell it what you want, right? So inputs go into it, stimuli from outside, its environment's acting on it, and you tell it what you want, and it outputs close to or something like what you want. That would be a good control system. A bad one would be one that doesn't give you what you want, right? So without control theory, there would be no robotics. Control systems are found in many biological systems that vastly predate humans. However, I mean, like, there are some really cool ones in humans, and if you're taking biomedical, I think, you guys might be talking about some of those. However, human-made control systems date back to around 300 BC. The Greeks built a water clock that included a float valve, similar to those in modern toilets, to control the volume of water in a tank. Pretty cool how that's still a relevant technology. It was a good design. Why mess with it? It still works. I mean, you don't really need a microcontroller to control your toilet. It's just not that important. Also, I think we use microcontrollers too often sometimes because we want to and they're fun. Okay. Liquid level control was the only type of control system until the 17th century brought steam, pressure, and temperature controllers. 18th century speed controllers were developed for windmills and steam engines. Control theory, as we understand it today, began in the second half of the 19th century with names you will probably recognize: Maxwell, Routh, and Lyapunov. They began applying mathematics extensively to control systems. And some of their methods are still in use today. You guys have learned about the Routh table, and we still use that. Still a good one. They began applying oh yeah, I already read that. In the 20th century, the gyroscope was used to automatically steer ships. Oh no. I have to go get my charger. I had my screen on blast the whole time. I shouldn't have. Yeah. Minorsky developed what would become PID control. Boda and Nyquist developed the analysis of feedback amplifiers and frequency response controller design techniques, which we'll talk about in this class. And Evans developed root locus techniques in 1948. The theories and techniques from this period are typically called classical control theory. Okay. Nice is mostly classical control theory. But there are some modern control theory ideas in it too. We'll talk about that. So finally, in the late 50s and 60s, what is known as modern control theory began, which is based on state space methods. So we know how to work with those, which is great, and we will do some state space control, but we're not going to get too in-depth into it. It is important to note that both classical and modern control theory are still widely used and complement each other well. Cybernetics is the study of control and communication in the animal and the machine. Okay? It's not really around anymore. It's sort of, it is. It's just sort of like changed names, and we'll talk about that. But it was originally called cybernetics. The general idea was to understand biological systems and create artificial systems that could perform autonomously in their environments, much like an animal or human. This field produced what is often considered to be the first robot, Gray Walter's tortoise. So W. Gray Walter was a neurophysiologist in and after the 40s. He built biomimetic, which means to copy or mime biology, turtle-like robots as shown below. So this is a photo. One of Walter's robots was named Machina Speculatrix, which means machine that thinks. It consisted of a photocell, a bump sensor, a rechargeable battery, 3 motors, 3 wheels, and 1 analog circuit. So like, not a lot. Notice no microcontroller was in it. It had the following capabilities. Find the light, head toward the light, back away from bright light, turn and push to avoid obstacles, and recharge battery. Those are the things it could do. Walter's robot used reactive control, which is control that uses prioritized reflexes, in quotes, to determine behavior. Later, we will learn more about reactive control, which can create animal-like robotic behavior. And this is like some of my favorite stuff in robotics is this stuff. Reactive control is really cool. And we're going to spend, there's a whole chapter in the primer on reactive control. That's pretty neat. Some of the behavior of these robots were rather complex, yet not programmed in. This is now called emergent behavior, and we will learn more about this later. So emergent behavior is like my jam. It's cool. It's really cool. So there's this video of Gray Walter's tortoises, and I'm gonna play it, and I'm gonna go get my laptop charger as I'm playing it, and I should make it back soon. I just need to not forget I do have my key. Oh, do we know if that key? That we don't even know because you guys can never get in that door. Never mind. All right, I want to play this. It's not working still?
Yeah, the close one.
Yeah.
I heard it's not working still.
Yeah. Okay, I gotta turn this up real loud. We don't have speakers in here, so. All right. See if I can make it back in 2 minutes.
In a simple villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small, and he doesn't dress them up to look like men. He calls them tortoises, and so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action. Mrs. Walter's pet is Elmer, Elsie's brother, in the darker vest. He works in exactly the same way. Dr. Walter says that his electronic toys work exactly as though they have a simple two-cell nervous system, and that with more cells they will be able to do many more tricks. Already Elsie has one up on Elmer. When her batteries begin to fail, she automatically runs home to her kennel for charging up, and in consequence can live a much gayer life.